Next one is there are some other applications are also there. So far just now covered the nozzle and diffuser part, nozzle and diffuser part, and the remaining things that is the compressor and turbine is there. So we will apply the compressor and turbine section, right? So go through the PKNAC textbook and very good things have been given there, or try to follow this particular lecture. So the compressor, so, right? So the compressor is nothing but the flow rate entering, that is low pressure fluid will be entering at this section, and a high pressure fluid is going to leave. High pressure fluid is going to leave, that is the high pressure fluid outlet. So what is the importance of a compressor? Compressor is nothing but it is going to increase the pressure at the outlet side, high pressure, right? Pressure at the outlet side. So the compressor, if you observe the reciprocating, there are when you talk about the compressor, there is various varieties of compressors are there. That is, the reciprocating compressor is there, rotary compressor, axial compressor, centrifugal compressor. But whatever it may be the compressor, you need to apply the steady flow energy equation. You need to apply the steady flow energy equation, right? So in the same way, that is this is the compressor. Here observe the inlet part and outlet part. If it is a turbine, then here this is the inlet point, right? So the mass flow rate of the fluid, which is in kg per second. Some flow rate of a fluid is entering at the inlet section of a turbine, and it is going to leave at the exit section. So this is the section 2-2, that is, this is nothing but the mass flow rate m2, right? And this turbine is gets insulated. If this gets insulated, then q, heat transfer, is nothing but equal to 0. So from the turbine, and when I talk about the turbine, the turbines, there will be the different things are there. What is that one? There, whether that particular turbine is a gas turbine or it is a hydraulic turbine, right? Hydraulic turbine, or it is a nuclear turbine, or it is a nuclear turbine, that is in nuclear power plants. So nuclear turbine, hydraulic turbine means hydropower plant, gas turbine means gas turbine power plant, and the another one is a steam turbine. Another one is steam turbine. So the turbine, whatever it may be the turbine, but there are different varieties. Gas turbine is there, hydraulic turbine, nuclear turbine, steam turbine is there. And what is the functioning of this turbine? Turbine is going to produce the net work output. So the turbine is going to give the work output, right? The turbine is going to give the work output. So that is W is positive. Whereas for the compressor, you have to give the work input. For the compressor, the work input is there. So that is, this is the work input, right? So here W is nothing but minus sign. Here W is nothing but positive sign. Here W is nothing but positive. And even in the compressor, there are the, the reciprocating compressor, and another one is the rotary compressor, and you can different varieties, just I am discussing, that is axial compressor, which is used in gas turbine application, aviation purposes. Axial compressor, and the another one is a centrifugal compressor, centrifugal compressor. So whatever it may be the compressor or whatever it may be the turbine, when you are applying, what is the steady flow energy equation? That is H1 plus C1 square by 2, right? C1 square by 2 plus GZ1, this is all closed, right? plus d bar q by dt is equal to h2 plus c2 square by 2 plus gz2 by gz2 plus d bar w by t, d bar w by dt. That means here for a turbine, it is a positive, right? So for a compressor, it is minus. This is what the student has to observe. But anyhow, this turbine is insulated one. So this particular turbine is the insulated one. Then in this case, the kinetic energy terms are neglected. Kinetic energy term, right? And this heat transfer is also zero. Heat transfer is also zero, and the potential energy is also zero, right? So what you are going to be getting, that is the W dot, that is this one. From the turbine, that is from the turbine, you will get it as a W dot is nothing but equal to M into, that is H1 minus H2, M into H1 minus H2. That means this is M means this is in kg per second. This is in kilojoule per kg. So kg cancelling. So kilojoule per second, it is nothing but kilowatt. So this is also kilowatt, right? So this is how you have to solve. If it is a compressor, then W dot you will get it as, that is H2 minus H1. Why? You have to give the work input to the compressor. Whereas the turbine is nothing but you will expect the work output from the turbine. So this is how you can you can apply the steady flow energy equation to this particular application. So the steady flow system, that is also covered. Steady flow, that is application of a steam turbine, or application of a compressor. Now here you should be alert while applying the correct heat transfer and work transfer relations to the open system. So these are all nothing but the open system, that is nothing but where I can also call it as a control volume technique problem. This is nothing but the control volume technique problems, right? So once this is over, then the heat exchanger content is there. Then the heat exchanger content. So in this heat exchanger, what is the importance of heat exchanger? The heat exchangers that you can define as in terms of two ways. That is heat exchanger. This is a heat exchanger, and this heat exchangers will be of two varieties. One is the direct contact heat exchanger. Direct contact heat exchanger. That means directly mixing the hot fluid and cold fluid. Whereas there is another heat exchanger, that is the indirect contact heat exchanger. So here the hot fluid is not going to mix with the cold fluid, right? So that means that the hot fluid is flowing around the pipes, whereas the cold fluid is see here, the cold fluid is going to pass through the pipeline. So this cold fluid is passing through the pipeline. Hot fluid is above the pipeline. So how we are going to apply this steady flow energy equation? So what are the terminologies are involving over here? So when you apply that here, that is this cooling water, WC, cooling water, which is in entering, and this steam is also entering. That is the continuity equation and the energy balance equation. So that is inlet part is nothing but equal to outlet part, and outlet part, So this is the inlet, identifying the inlet part and outlet part. What is the inlet part? That is inlet part is WC, right? So that is flow rate of a cold fluid, flow rate of a cold fluid at the section 1. So that is nothing but H1 plus the steam flow rate. Here, this is also the entering case. So that is the weight of the flow rate, that is a steam flow rate into H2 is equal to, then at the exit section, the cooling water flow rate is there, that is WC H3 plus this is the exit and this is the also exit. So that is the flow rate of the steam into H4 into H4, right? So separating the steam terms and the cooling water flow terms. So the steam flow rate, if you take the steam flow rate, that is this one, H2 minus H2 minus H4, that is equal to the cooling water flow rate H1, that is outside. So this H3 minus H1, right? Or you can also use that mass flow rate of a steam H2 minus H1 is equal to mass flow rate of a cold fluid H3 minus H4. Because already we have covered that this internal energy is a function of a temperature, right? And enthalpy, that is also the function of a temperature. Enthalpy is also function of a temperature. So that means here it is a function of temperature which is going to occur at constant volume, specific heat at constant volume. This is going to occur specific heat at constant pressure. So CVT and this is CPT. Now you can use this particular case, that is the mass flow rate of a steam, and this H is a function of a steam, that is here Cp, that is specific heat of a steam, Cp, yes, specific heat of a steam, that is here. The steam is entering here. So that is Cp T2 minus T4 is equal to mass flow rate of the cold fluid into specific heat of the cold fluid, it is 4.186. And this is going to be mentioned, right? Specific heat of a cold fluid is 4.186 kilojoule per kg into T3 minus T4, because enthalpy is a function of a temperature. So you can use this particular relation in order to solve this particular thing. Why here the kinetic energy terms are neglected, potential energy terms are neglected, no heat transfer and no work transfer. So here because this is not at all going to do any kind of a work, and the heat transfer, it is a perfectly insulated heat exchanger. So W dot is equal to 0 and Q dot is equal to 0. Indirect contact heat exchanger, right? So this is the indirect contact heat exchanger. This is the indirect contact heat exchanger where the hot fluid is not going to mix with the cold fluid. So in that case, when you apply the steady flow energy equation, so the steady flow energy equation at the inlet part is equal to steady flow energy equation at the outlet part. And in this connection, the kinetic energies, potential energies, and the heat transfer terminologies are neglected. And in this outlet part, the kinetic energy is neglected, potential energy is neglected, and the work, that is you cannot get work output from this heat exchanger. So work is also 0. So this is the outlet part and this is the inlet part. So these terminals are connected, disconnected. So this is the energy balance equation, and when you apply this energy balance equation, this is how you can find out the other temperatures by knowing the 3 terminal temperatures, right? So this is the steam condenser. So this you can also call it as a steam condenser. So this is a steam condenser is nothing but one type of a heat exchanger where hot fluid and cold fluid are not going to mix up. Just only there is a heat exchange is going to take place. So heat exchanger is nothing but it is a device to transfer the heat from hot fluid to the cold fluid. Whether it is a direct contact or indirect contact, based on the application point of view, we may use this particular cases, right? So that is what the heat exchanger. Hope this particular concepts are clear. So how you can apply the steady flow energy equation? So this particular things you can get it. So this is the diagrammatic sketch you have to draw and write down the steady flow energy equation and what are the terms can be neglected, what is the inlet part section, what is the outlet part section, what are the terminologies or whatever the variables which are negligible, find out that one and finally deduce the steady flow energy equation to that particular application. So in most of the, that is especially when we talk about the steam condenser, in steam thermal power plant, this steam condenser is used, where the condenser means it is going to condense the steam from gaseous, that is from the hot condition to the liquid state condition. That is a saturated vapor state condition to the saturated liquid state condition. Saturated vapor state condition to the saturated liquid state condition. So that the student has to understand. And already I have covered the perpetual motion machine of first kind. So no meaning to cover into this particular side. So hope now you have understood this particular concept. So thank you one and all. So for today's class, just only I have covered understanding level of the steady flow energy equation applied to the open system. There are many realistic situations are there. So that identifying the realistic situation and in most of the industries, this engineering devices, these are the equipments are using. So when you apply the steady flow energy equation, how the steady flow energy equation can be deduced to that particular application. So that is the significance of this particular point. Thank you one and all.